we are going to determine the stability of the pendulum. This is what a typical problem statement for it here. And then we'll look at pendulum equation. This is a force free body diagram for the pendulum. And this pendulum shows typically masses, what are the masses in the gravity direction. That is what an mg force will be in downward direction. This is mg cos theta will be taking care of the tension, and mg sin theta is taking care of restoring force. It is a kind of a restoring force. Here it is a actually equation for this, and in this we have included this also viscous force. Viscous force, or we can say it is a force which will create a damping into the system. That is what the thing. So to convert into the MATLAB, we are using an ODE solvers. In this ODE solver, we need to provide a first order differential equations, and that's what we need to convert. This is a second order equation, and need to convert into first order equation. Here it is mg sin theta is converted. Sin theta is in a transcendental equation. This creates a non-linearity into the equation. That's what it is converted into linear equation, that is theta. But we are taking sin theta as it is, and we want to solve it the way it is possible here. So for that purpose, we need to assume first of all x1 is equal to theta, x1 dot is equal to x2. These are nothing but a kind of a steady state equations we are going to convert. x1 dot is equal to x2, and another equation is x2 dot is equal to what are the rest of the equation. That is what we want to convert it. And these two equations, x1 dot is equal to x2 and x2 dot is equal to this entire equation, is now converted into a kind of a function, and will be used into simulation of the pendulum equation by for an ODE solvers. So for that purpose, we'll now look at what is the way we can execute this pendulum equation. In this pendulum equation, first of all, we need to develop a function for pendulum. Means what are this x1 dot and x2 dot. These two function derivatives need to be determined and to be simulated, and that is the way it is written as a function for pendulum. And we need to define how much time we want to simulate it. That is what it is called as a time span. Next is we want to define an initial condition for it. Okay, sorry. So initial conditions, we need to define how much, what is the initial condition, and based on that we want to simulate. And then we are using an ODE solvers, that is maybe 2, 3 and 4, 5. We will we'll observe the difference of the results of ODE 2, 3 as well as 4, 5 functions, and then we are going to solve within a time scale and determine the results for it. So we'll now move towards a MATLAB part. So this is what an entire MATLAB part. So first of all, we'll define in one function here. Function phi. I think some problems are there. Okay. Okay. And it, I think. Okay. It is. So we will create a one function folder. So I will say it is in a pendulum as in a folder, and we'll what are the files we are going to use it. We want to create. What are the files you are going to create it? So those files will. Let me mute. And we'll start with a new script file. First of all, we need to start with a function as in a name as we know it, and output from this file is nothing but an x1 dot and x2 dot, and these two will be embedded into one single variable, that is what an x dx. Okay, which is equal to, we are going to give a pendulum pend as a function name, and we want to provide an x as an initial condition for this and t as a time scale for this. X also contains two variables, one is an x1 and another is an x2, which are the function we created. We can write in this function simulates pendulum equation. This is what help we can use it. Then we can now start writing dx1 means it is an x1 dot, which is equal to x of 2, which we know it here as per your equations. So here it is an x1 dot is equal to x2, and here it is an x2 dot is equal to what are the entire function. So similarly, I'll write in a second equation dx of 2, which is equal to what are the t, capital T, that is tt, I will write minus equation is g divided by L into sine of theta. Okay, theta is nothing but here. Now instead of theta, we have assumed that is an x of 1 is nothing but a theta minus ct is nothing but a damping coefficient into x of 2. So that is what two equations we have written. But these are tt is nothing but a function. So tt is nothing but a function which is t0 into sine of omega into time. This is nothing but a forcing function. So for that purpose, again we need to define what is my t0. Initially we want to simulate only within free vibrations. That's what we'll keep t0 is equal to 0, and also omega is equal to 0 also. Okay, so this way this function is completed. Then another one is unknown is g is equal to 9.81. It is in meter per second square. That is what value of gravity. L is equal to, will take 0.1 as in the length of the entire pendulum. Then again CT we need to provide. CT also will consider damped free system. That's what initially will keep it 0. So this way your function is ready, and for function, for this we need to have a transpose of it. Reason for this, because ODE solver needs a matrix into the rows, and whatever we created in a rows matrix, actually it needs in a column vectors. That's what it is converted. Then now save this function. As in a paint name. After saving this, now you need to use this function as an ODE solver. Then now create another function, simulation pendulum equation. Then as usual we need to clear all the workspace, then clear the screen. Then we need to define inputs. So these inputs are t-span, that is what we want to start the simulation with 0 second to maybe 10 seconds something. Okay, then also we need to provide an initial condition, that is theta. Initial condition I will provide theta as a 1 initial condition, so which is 0 here. Then d theta, that is it is a second order equation. That's what we need to have two initial condition, theta and d theta. Then altogether these two initial conditions to be clubbed into one, theta and d theta. Okay, but these theta and d theta normally we give into the angles, but our MATLAB function, that is sine, we are using, it is in radians. That's what we need to convert that into the radians. Theta is equal to pi divided by 180, that is pi into theta divided by 180. So similar fashion you can work out for d theta also, because that is also in angular we are going to give it. So I'll change only d theta here and same formula will be used here. After doing all this, we need to now ODE solver. In this ODE solver, what we can do it? We need to take an output as in a time as 1, another as an x as an that is x1 and x2. x1 means theta and x2 means d theta, that is derivative of time, theta dot velocity. So now I will use an ODE 2,3 as a solver. Then I need to whichever the function we created, that is what an append. So that is to be used. Then I need to give an a t-span. Then I need to give an a, after the t-span I need to give an initial condition, that is what an x, or you, instead of x you write an x0 something. So it is better because most of the time we define initial condition as an x0. Then this is what an ODE solver will do a simulation for you. After that we want to separate out, because t contains only one column, x contains two columns, one is x1 column and another is an x2 column. So that is to be separated out. So that's what we'll see in our results. So these all results come into the radians, because we have converted theta into radians and again we need to convert that into degrees. So that is what also we need to do it. So now I will write in a theta 1 which is equal to output. I can say it is, instead of theta 1 I will say it is an output out, which is equal to x. Separate out the first column and put into this. So after separation we need to multiply this with an 180 divided by pi, because it's in radian, you need to convert into degrees. Similarly we can work out for d theta out, and here it is in a column is second. So now we can go for a figure number 1. So that is what a result you want to see it. So I can plot t versus theta underscore out. So this is what then rest of the things is x label, time in second, then y label, that is a angular displacement in degrees, and then you provide a grid down. So similar fashion you can copy it down. We can copy down this for a second figure, which will plot d theta, okay, out, and here angular displacement. Instead of angular displacement we can write in a velocity, okay, that is in degree per second. So we'll now simulate this using an ODE 2,3, and before that I'll write this paint simulation, okay, and then we'll simulate this and we'll see the results, how the results are coming. So here we are not provided any initial condition, this is one thing. Also we are not provided any kind of an so some error is there as usual. So it is going to access this index out of bound x of 2, x of 1, pendulum equation, okay. We are not provided x here as well as t here, maybe so instead of this I will write here x0 t span. I think just let me see in a help ODE 2,3. This will tell you there may be some error. Maybe this sequence is wrong, x0 here and then time span. I think that will serve our purpose. We'll simulate and will work out. Okay, that error is change must be different from first entry. Okay, t span and this maybe. Okay, ODE here, this is a time span is there, and this is what an initial condition. It's correct, no issues. I will initially put it 0 0. This is my 0, and initially I will put it 0. Maybe some another error will be there. We'll simulate and we'll see it. Maybe okay. So that is what it is going to do it. Here I need to provide t span first, and then I need to provide an x0 as an initial condition. Something is wrong, I think. X of 2, dx of 2, pendulum equation, tx of 2. Okay, somewhere t and x, I think here. T and x. I'll save this. Think that has solved our purpose. Yeah, it is now doing a work. So it was happened because we need to provide here first argument should be a t here, and then that is what basically rule it for pendulum that in ODE solvers. So here we got an initial condition as a 0, and that's what your angular velocity and angular displacement is showing to be 0. We'll now provide some in angular velocity. Maybe here I will write it theta and d theta. So here it is in a d theta. Okay. So here I will provide an angle as an 5 degree as an angle, and we can just observe one simulations for this. So it is now starting within a 5 degree. Velocity is also starting within a 0. So whatever the time span is larger enough, so we'll reduce it to the 5 cycle so that we can see a single loop of simulation. So here you can just observe it is starting within a 5 degree, and here it is starting within a 0. That is what it is, initial condition simulation. So if I go for more simulation, more time simulation, you can just observe that output is going to be reduced, but actually we are not provided any damping. So this is due to a truncation error in the simulation. So to avoid that, we need to go for a higher order ODE solver. That is what 4-5 you can go, and that will serve your purpose. So you can just observe it is now not showing any kind of damping into this. Okay. So this is what a simple simulation, undamped simulation. So when you want to provide a damping into this, so now we just look into the function where pendulum function is there. So here it is on a time. Here it is a forcing functions. That is what these are the two elements which will be used for to generate a forcing function for this. So here we have provided a damping, that is 0. We'll provide a 5 as a damping here and save this function, and then again come back to your original file and then script file and then run it. So here you can observe the damping into this. So this is what shows on a simulation, how to simulate this. So one more plot is to be drawn, and so that is what on a third plot I can say. That is what a theta versus theta out. Theta out versus theta d theta out means on one axis, x-axis, I am plotting angular velocity, angular displacement, and another y-axis I am going to plot on angular velocity. These are nothing but in a state of your system, and we want to observe whether how these states are behaving under damped condition. So you can just simulate this and you can observe. So here it is nothing but an initial condition it is given 5 degree, and your velocity on vertical axis velocity is source. So per cycle it is going to absorb the energy, and after some time it will go to and get it settled into the equilibrium. This is nothing but a 0 0 condition for angle as well as velocity. It is a 0 0. So this is nothing but an equilibrium for your system, and this goes and settle down it into this. If I provide a damping, zero damping, so this graph seems to be something elliptical. The reason for this elliptical graph, you can see it. So this is nothing but elliptical graph. It oscillates because there is no any other element which will absorb the energy into the system. That's what it is going to show you this only circular or elliptical shape for this. So we'll now look at the, so this is what on a simple pendulum without any forcing function. We'll now look at how to simulate the forcing function. So here I will keep on a damping somewhere. It is in a maybe in a somewhere one or something. So lower damping I will prefer for it because I can observe more in terms of a transient response. I'll provide in a 10 as in a forcing function or 10. Then amplitude I will provide in a 5. Natural frequency I will provide maybe in a somewhere 10 omega, and that is a 10 radians per second. And then here we need to remove this initial condition because in forcing condition there is a 0 0 initial condition. That's what I'll keep I'll keep this initial condition to be in a this is a time span, and this initial condition I'll keep it 0 0. And then now simulate this and observe the what is going to happen into this. This is what on a transient response you can observe it, and we need to simulate for more time, maybe in a 50 seconds or something. So during that you can observe transient coming into the system. So this is the phase where you can observe the vibrations are more compared to this. What are the amplitude of vibration is the same here. For this case, it is somewhere it is going higher side and then coming to in a steady state. This is what in a steady state vibrations, and this is what in a transient phase of it. So this is the way you can simulate any pendulum equation or any kind of an ordinary differential equation for this. One more thing I would like to tell you here, important thing. So you can simulate an even what it is called bits phenomena. In this bit phenomena, we need to determine what is the natural frequency of system, and if your forcing frequency is near to your natural frequency, and you can see these bits, you can observe the bits into this. So if you look into the equations, in this equation, so natural frequency is nothing but a G by L. So this is what a G by L shows on a natural frequency square. So I can now determine here natural frequency. I will take this GL upper side so that I want to include into this. I will determine omega underscore n, which is equal to square root of G divided by L. Okay. So this natural frequency, I am going to now provide a 90% of its natural frequency as a forcing function. That's what omega underscore n. So this way I can now provide a forcing function, and now I will simulate. You can just observe, and there is a bits you can observe it. So I need to again increase some natural frequency, not 90, but I will increase it to the 95, and then save, then simulate it. Yeah, it should come, I think. Omega root over square root of G by L. Is that correct? G by L natural frequency of your pendulum is in G by L, I think. Okay. So, but if you go into the detail, you can observe it, and this bits phenomena also you can observe into this. So this is for entirely for today's session. Similar kind of a simulation also you can work out, and it's in a very simple one. You can work out similar fashion, that is a spring mass damper system or any kind of Van der Waals equation, so many other equations also you can simulate it. So thank you for today's part.